today, as I mentioned earlier, that we shall start with the quantization of the electromagnetic field. And so, before we start quantizing the electromagnetic field, let us recall what are the Maxwell's equations in the absence of sources, that is external charges and external currents. So all of us know that the absence of external charges and currents, that is sources, Maxwell's equations are as follows. These are the equations, and then we also have curl of E is minus 1 by C, then P, and curl of B is 1 by C, then P. So these are the four Maxwell's equations in the absence of external charges and currents, and you know that Maxwell theory has gauge invariance, and therefore you have a gauge field. This is the gauge field. So the derived component is 0, and this is di, where I runs from 1 to 3, and mu runs from 0, 1. And we also know that what we shall do is we shall try to quantize the electromagnetic field in the Coulomb gauge. We shall later on see how we can carry out, since electrodynamics is a covariant theory, is a relativistic theory. One should quantize this theory in a covariant way, and since it also has a gauge invariance, therefore your quantization procedure should be covariant. But what we shall do in this lecture, at least to start with, is quantize electrodynamics in the Coulomb gauge. This is what we want to do. And in the Coulomb gauge, so let me write down what this is. So what we shall do is, we know that the zeroth component of A, mu, is basically the scalar potential, and this we shall set to 0, and del dot A we shall set to 0. One can actually, you know that this is called the Coulomb gauge, divergence of A is equal to 0, and with these two things it is called the transverse gauge. And you have already seen this gauge in your classical electrodynamics course, but you can actually also argue that why in the first case, why you can take this gauge at all. So you can show the reachability of this gauge, which is known as the transverse gauge or the Coulomb gauge. So what we have done is we have set the Coulomb gauge, and in the Coulomb gauge, we know that E is basically minus grad phi minus 1 by C del A del B, and since we are in this gauge, therefore in this gauge it becomes minus 1 by C del A del B. So this is what we have, and you see that this is consistent with the fact that divergence E is equal to 0, because if I take a divergence of E, then this must be 0, and this tells you that divergence of A should be equal to 0, which is nothing but the Coulomb gauge. So this actually tells you why this gauge is actually, one can take this gauge in the first place. So we shall work in this gauge, and the next thing that we should note is the following, is that this vector potential, this is basically the free vector. In ordinary vector notation, you write this as A vector. You can show easily, you must have seen in the electrodynamics course that the free vector or the vector potential, free vector potential basically satisfies a wave equation. So this is basically del 2A del 2, that is Laplacian of CX. So this is a wave equation that is satisfied by this vector potential. Another thing that we would like to note is that this follows from standard electromagnetic theory, and we also note that the Hamiltonian density is basically given by 1 by 8 pi E vector square plus E vector square. The units in which the Hamiltonian you have this factor of 1 by 8 pi in front, these are called unrationalized units, and in these units, the fine structure constant is basically given by E square by 8 bar C. This is the Sommerfeld fine structure constant, and in these units, in which you have this factor of 1 by 8 pi, fine structure constant is E square by 8 bar C. In QED, quantum electrodynamics, which we shall look at later, in QED, the Hamiltonian density is basically, this is the standard form that one uses in QED, half of B square plus B square, and these are called rationalized units. In rationalized units, the Hamiltonian density you don't have the factor of 1 by 8 pi, rather you have a factor of 1 by 2. And in these units, the fine structure constant is basically E square by 4 pi H bar C. So these units are called rationalized units. In these units, in the rationalized units, the Hamiltonian density takes this form, and the fine structure constant is this. In unrationalized units, which we shall use now, you can actually use this also, but we shall use this thing for the time being. So in these units, alpha is this, and Hamiltonian density is this. So this is so far about the background of standard electromagnetic theory. So you have the Maxwell's equations in the absence of any forces, in the absence of charge, external charges or currents. Then you have the vector potential, the 4 vector potential mu. So this you have because you have a gauge invariance. Because of the gauge invariance, you have this, and then you fix the Coulomb gauge, the transverse gauge A0 is equal to 0, and E vector is given by this, and in this gauge you have vector is equal to this. So this is what we have, and then we have the wave equation satisfied by the 3 vector potential. The Hamiltonian density is this in unrationalized units. In QED it is this, where this fine structure constant is of this form. So now what we shall do is, our first thing is to find out a solution of this wave equation. That is the first thing which we would like to do, to get a solution of this wave equation. And to get a solution, the standard way that we employ is the following. A vector is a function of x and time t. So what we do is just carry out a separation of variables. So we take xi t and a vector mod x. So our aim is to solve this wave equation. So what we are doing is standard classical field theory. We are looking at classical electrodynamics now, and we want to solve this equation and see what happens. So if you take a separation of variables of this form and substitute this in this equation, what we shall get immediately is the following. We shall get z2 xi zt2 a0 x that is equal to c square psi t. Then we have Laplacian of a vector. So you have a vector over here, it's a function of x vector. So this you can easily see if you just substitute it over here, and then formally you can write it in this way, that 1 by psi t d2 psi d2 is equal to c square a naught x vector Laplacian of. You see, you have a vector sitting in the denominator, but this is just a formal way of writing this equation. This is not very defined, 1 by a vector quantity, but this is just a formal way of writing this thing. So you will have something like this, and then what you can do is you can take this to be minus omega square, because we want to look at oscillatory solutions. We don't want to look at decaying solutions. So you take this to be equal to minus omega square is the constant. The way you do in partial differential equations, this must be some constant which is independent of time t, also independent of x. So if you take this, then what we shall get is d2 psi dt2 plus omega square psi is equal to 0. Since this has to be a constant, because this is only a function of time t and this is a function of x vector. Therefore, if you just differentiate this with respect to x vector, say, that must be 0. So, which tells you that this constant, whatever you get, whatever number is here, it must be independent of x. Differentiate this with respect to time, it will be 0. So, this tells you that this number should be independent of time t. Therefore, this is independent of t and x. Therefore, it is a constant. So, you have this equation, and also you will have another equation which is so now we go to the other side of the board. So the other equation that we get is Laplacian of A, this is equal to plus omega square by c square A will be equal to 0. So we have two ordinary differential equations which arises from this partial differential equation, and if you solve this, what you will get is psi t will be to the power of minus I omega t, and to the power of plus I omega t. So this is what psi t is, and if you assume that your electromagnetic wave is basically a wave with polarization epsilon vector, it is basically a vector. This epsilon vector is a vector in the direction of a vector, right? So it is a vector which is proportional to this a naught vector. So that is what this epsilon vector is. So if you assume that your electromagnetic wave is a plane wave with polarization, epsilon vector, and moving in the direction n cap, such that k vector is basically equal to k n cap. So this is the direction in which the electromagnetic wave, plane wave, is moving. Then this a0 vector, function of x, you can write it to be a0 epsilon vector e to the power of I k dot x. Just a minute. Hello. Okay, so this is basically this tells you that the electromagnetic wave is a plane wave. It has a polarization epsilon vector and it is moving in the direction n cap. So you have this thing, and now you can therefore write down the full solution of this wave equation that you have. The full solution of this wave equation is the following. So now you can therefore write this down as okay. Another thing that we should now do is the following. Now, once you have the solution of this A0 vector, now you assume that the electromagnetic field that we have kept the electromagnetic field is in a box of volume V and impose periodic boundary conditions. So if you do that, then what, as before we have seen in the case of the real scalar field, that these k values will get quantized. Not quantized, it will take discrete values, because there is, we should not say quantized because there is no quantum mechanics here. The fact that the k values will take discrete values is due to the periodic boundary conditions that you impose. So once you impose periodic boundary conditions, by keeping the electromagnetic field in a box of volume V, then these k values takes discrete values. So let me write down one of the components of the k vector. So
Sir, the board.
oh, sorry, I've not changed it. Sorry. So now is it okay?
Yes, sir.
Okay, good. So what you will get is, so as before, what you do is impose periodic boundary conditions, and therefore e to the power of I k dot x, you just consider it as e to the power of I k x x, and impose the periodic boundary conditions along the direction x. If you do that, then your kx will get values like this, where n will be plus minus 1, plus minus 2, and so on. Okay, and similarly for ky and kz. So you impose periodic boundary conditions on all the three sides, and then your k values will get discretized. And once you have this, now you can write down the full solution for your a vector. This thing. So a vector can now be written as summation over k vector, where k vector takes the discrete values, kx is given by this, and so on, ky and kz. Summation over k vector, and then we will have a0, we have the polarization vector epsilon, and then we will have e to the power of I k dot x is the plane wave minus omega kt should 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 the this. And another thing is that here this omega c square by c square, this is basically k square. So let me write it on this side. So omega square by c square, this is equal to k square. Okay. So this actually gives us omega is equal to ck. That is what we should have for a electromagnetic field. Okay. This is the standard dispersion relation that you have. And therefore, this k vector that we have here, this k vector is basically k n cap. So the electromagnetic wave is propagating in the direction n cap with magnitude k. The magnitude k is actually given fixed by this. It is basically omega by c. Okay. Plus e to the power of minus I k dot x minus omega k. This is what we have. So you can see that A vector is a solution of this form. So since this is a linear differential equation, so what we have done is apply the principle of superposition. You get one solution, so this is one of the solutions, and then you take the sum of two solutions for two possible possibilities, e to the power of minus I omega t and plus I omega t, and e to the power of I k dot x and e to the power of minus I k dot x, combine them, and then you sum over all k. So this sum over all k is possible due to the principle of superposition. So this is the most general solution that you can get for the electromagnetic field. You will not have a solution for A0 because A0 we have already fixed the gates. A0 is 0. So only thing that remains is A vector. Is this okay? Is this clear?
Yes.
Okay, now you can have a look at the full code. So what we have done is we have said that this omega square by c square is k square, and k is the magnitude of that wave vector. So k vector is the wave vector, and it also tells you the direction in which the electromagnetic wave is propagating. And k is basically the magnitude of this k vector. So this is the magnitude of the wave vector, and omega is the energy related to k in this way. Omega is equal to ck. Okay, now let us proceed further. Let us now recall that this solution that we have written down must be compatible with the Coulomb gauge. So we must have divergence of A is equal to 0. And this gauge is actually compatible with the fact that E vector is minus 1 by C del A del T. And if divergence E is equal to 0, then divergence A must be equal to 0. So you can understand why this gauge is reachable in the first place. It is a valid gauge. And what I am saying now is the following, that this solution that I have given should be compatible with this condition. So if you take a divergence of this equation that we have written down, what we shall get is the following. You can immediately see that if I take a divergence of A vector, then you will have ik coming down over here, and this would immediately give us k vector dot epsilon vector equal to 0. So the condition that follows from the Coulomb gauge with the fact that divergence A is equal to 0 is that k vector dotted with the epsilon vector, the polarization vector, should vanish, which tells us that the polarization vector, epsilon vector, and this polarization vector is actually proportional to A vector, and the electric field vector is also proportional to the A vector because electric field vector is minus 1 by C del A del T. So E vector, A vector, and the polarization vector, all of them are proportional to each other. Okay. By proportional, I mean that you have two vectors there from the same direction. Okay. So this tells you that the polarization vector as well as A vector and the electric field vector are all perpendicular. All of them lie in a plane which is perpendicular to this direction of propagation of the electromagnetic field. So this tells you that epsilon vector is perpendicular to k vector, and k vector is nothing but the direction of propagation of the plane wave, plane electromagnetic field. A vector is also perpendicular to this, and E vector is also perpendicular to this k vector. Okay. So this immediately follows from the Coulomb gauge condition, and now you can see that something interesting has occurred already, because what we have done is that in the transverse gauge, A0 is already 0. We have fixed it. And you can actually show, you can argue that A0 is equal to 0 is a reachable gauge. You can take it. This also we have given an argument that this is also a reachable gauge. You can fix it in that. So this is a Coulomb gauge. And so from this analysis, what we find is that when you fix A0 to 0, you have three components of A vector, right? There are three components, A1, A2, A3. But this condition tells us that A vector lies in a plane perpendicular to K vector because K dot epsilon is 0. Therefore, K dot A is also 0. Therefore, A vector is such a vector that it lies in a plane perpendicular to K vector. Therefore, effectively now we can say that there are only two independent components of A vector. There are only two independent components. The component which is along the direction of K vector, that is not there. Right? Because this one, if there is a component which is along the direction of K vector, then this condition will not be satisfied. This will be non-zero. The fact that this condition is there, it tells you that A vector is such a vector that it lies in a plane perpendicular to the direction of propagation of A vector. So effectively now we can say, so if you choose n cap, for simplicity, if I choose n cap to be along the z direction, so it is something like z cap, it is along the z direction, then A vector, then A0 is already not there because we have chosen it, it's a gauge fixing. And from this condition, it tells you that the A3 component, which is the component along the z direction, is also 0. And therefore, A vector has only two non-zero components, which are A1 and A2. And this actually tells you the transverse nature of electromagnetic field. That is why we say that electromagnetic wave is a transverse wave, because already you can see that the fact that the polarization vector, the electric field vector, is in a plane perpendicular to the direction of propagation of the electromagnetic wave. Therefore, E vector, we know that it is perpendicular to k cap, to the direction of propagation. And what we shall show next is that the magnetic field B vector, which is nothing but curl of A, is also perpendicular. It is mutually orthogonal to E vector and A vector. That we shall show in a moment. So let us proceed now. So you can see already that A vector has only two independent components. Therefore, it is a transverse wave. And now let us calculate from this. Let us calculate what E vector is. Let us get an expression for E vector. Okay. So once you have, we have the expression for A vector. So what will be E vector? E vector is nothing but minus 1 by C del A del T. So we just need to take a time derivative of this equation. If you do that, you will get minus 1 by C summation over K A0 epsilon, and then you will have minus I omega K e to the power of I is plus I omega K from this term, and then you will have e to the power of minus I So this is the expression for the electric field vector, which is minus 1 by c del L T, and you get this. And from here, we can write this as summation over k a0. We can take this I omega k common, so we write epsilon. So this will be what? If I take this outside, there will be a minus over here, and this minus will be I omega k by c. Omega k by c is nothing but k. Omega k by c is k, the magnitude of the k vector, that is k, and then we will have exponential I k x minus omega k t minus complex conjugate of this term, right? This is what we shall get. And now you can write E vector as this E vector in the following way. You see that this divided by 2i, so, or you can keep it for the timing, let us keep it in this way. Let us not simplify it further. So what we can do is, we can write straight away this thing as a ek vector. Okay? We can write this like this, where ek vector is just the portion that is inside the summation. And now let us compute what B vector is. The magnetic field vector is related to the three vector potential in this way, this curl of A vector. We already have the expression for A vector. Therefore, this will give us summation over k, k0 so E vector is this and the A vector is this, therefore I will get. Okay. So what we shall get is the following. You will have an I over here, A vector cross epsilon vector times e to the power of I k dot x minus omega k t minus e to the power of minus I k dot x minus omega k. So this is what you will get for the magnetic field vector, the expression, and you can write this k vector as n cap times k, because it is moving along the plane wave, moving, propagating in the direction n cap. So from here, what we get is the following. This n cap it is independent of this k vector, so you can just take it outside. And the remaining thing that you have here is nothing but summation over k ek. And there is a cross product obviously. And therefore this is nothing but n cap cross e. And we have actually proved. So you can see from this equation that the magnitude of the magnetic field is the same as the magnitude of the electric field, because this n cap is a unit vector. And B vector is actually, so you must have arrow. And each one, there will be arrow on top. Correct. This is there. There will be also an arrow here. Thank you. So E vector is summation over K, E vector K, and also here there will be a vector sign which I missed. So now you see from this equation, we have already proved that K vector, epsilon vector, E vector, K vector is actually perpendicular to these two vectors or these three vectors, so to say. From here we can see that B vector is perpendicular to both the electric field vector and the K vector, and n cap, which is nothing but K vector. So from this equation we can therefore conclude that B vector and K vector are mutually orthogonal to each other, are mutually perpendicular to each other. Is this clear? And also you can see from here that modulus of P vector is nothing but equal to modulus of P vector. So from here we can see that P, B, K are mutually orthogonal to each other, and we have also seen that A vector has only two independent components, and A vector, E vector, epsilon vector all are perpendicular to the direction of propagation of the wave, electromagnetic wave, K vector, and A vector is a vector potential. It is actually it is proportional to the polarization vector, epsilon vector, and E vector is also proportional to A vector. So you will see that the direction of the electric field is actually, you have this electromagnetic wave which is propagating along the z direction, and the electric field vector and the magnetic field vector are perpendicular to this direction of propagation. It is the direction of the vibration of the electric field vector that is taken to be the direction of polarization of the electromagnetic field. And that is due to this reason that A vector is proportional to the polarization vector and E vector is also proportional to the A vector, and therefore it is proportional to the polarization vector. So the direction of the electric field vector is the direction of polarization of the electromagnetic field. And how many independent polarization directions are there? There are two independent directions. There are two independent directions of polarization for the electromagnetic field. So, with this background, now what we shall do is calculate. See, in this, the expansion that we have written down for for the vector field A vector, that is totally fine. What is our aim? Our aim is to write down in Fourier or normal mode expansion for the in the quantum case when your vector field A vector is an operator. So we want to write down a Fourier expansion for that. But now we are not looking at the quantum case, we are at the classical level, and we want to write down a Fourier mode expansion for the or plane wave expansion for the vector field. But in the expansion, you must have noted by now that in the expansion that we have written down for the vector field, there is a constant which is A0. We have still not fixed this constant. So we have to fix it in some way. And we shall do it now. Let us do the fixing of this A0. Is this clear?
Yes, sir.
Are you following, or you must have seen these cases already in electromagnetic theory? So now let us look at, or let us calculate a quantity which is the energy density U of a single photon. We should not say photon, because the photon picture comes when you quantize the electromagnetic field, but we just use this photon language in a loose sense because we know what photons are. So let us calculate the energy density for a single photon of the incident radiation, and that would be given by something like this: 1 by 8 pi. What is the energy density? It is E vector square plus B vector square. But for a single photon or a single mode, these are EKs are basically the various modes corresponding to momentum k vector. Okay, so there can be infinitely many modes. So for a single thing, you have EK square plus BK square. Okay. Let us calculate this quantity. We have the expression for EK and BK, and we also know that the magnitude of E, not only the magnitude of E and B are equal, the magnitude of EK and BK are also equal. And therefore, this will become 1 by 4 pi EK squared. Okay? So if you calculate, you know what EK is. So if you calculate this, it is very simple to calculate. What we shall get is 1 by 4 pi. And from the expression of EK, what we find is that we'll get A0 square K square. If you look at the expression for EK, you will get A0 square K square, and then you get 4 factor of 4. Then you will have sine square K x minus omega. So this is what we shall get. Okay. And also, I think I have missed a factor of, or maybe I have not missed, everything is fine. Okay, so this is fine. So this 4 and 4 cancels, and k square is nothing but omega square by c square. So this will give us omega k square by c square A0 square sine square k dot x minus omega k. It is better not to say for a single photon because the photon picture is still not there. It is better to say that it is the average energy density of a single mode, of a single normal mode, so to say, of the photon, of the electromagnetic field, not photon field, of the electromagnetic field. So this is the average energy density for a single mode of the electromagnetic field. Okay. Now, let us calculate.
There should be a pi underneath it.
There
Should be a pi.
Good. Should be a pi. Good. I missed the pi. There should be a pi. So we just go back to the front part of the board once again. So there is a pi. Thank you, Shoal. This is the pi. Good. So now let us calculate from here, from this expression, let us calculate the time average of this average energy density for a single mode of the electromagnetic field. So let us calculate time average. So I denote that time average in this way, and this is nothing but integral over a complete cycle, basically this T by integral 0 to T. Let us calculate this. So this will give us 1 by T integral 0 to T, and this will be A0 square omega. I'm not writing the suffix anymore. I'm just skipping the suffix. let me just write omega square by pi c square, and then we have sine square this dt, and we just need to do the simple integral 1 by t. These are constants, you can take it outside. This I can write down as 0 to t dt by 2, a factor of 2, 1 minus, let me just check, it will be 1 minus cosine of cos of 2 k dot x minus omega t. And then you have to do this integral. This will give you a sine of 2 k dot x minus omega t divided by some factor, and okay, so this will just give you divided by 2 omega, which is a constant, you don't need to worry about that. And then you have to evaluate it between the limits 0 to t, and since this is a complete cycle, this is a full time period over which you are averaging, this factor, the contribution coming from this factor will cancel out, that will be 0. So you will get only a t from this integral, and t will cancel, and the final result of this thing will be a square omega square by 2 pi c square. This is the final result. Okay. So this is the time average of a single mode of the electromagnetic field. Time average energy of a single mode of the electromagnetic field per unit volume. So it is the time average energy density. But this thing, now we shall do a little bit of cheating, because we have not done any quantum mechanics so far. There is no quantum mechanics here. Everything is classical, no quantum theory. But now at this point we shall cheat a little bit. We will say that, okay, this is for a single mode, and single mode means a single photon, and therefore this average quantity, since it is for a single photon, therefore we will, at this point we shall say that this average is nothing but h bar omega by volume v. So now at this point we are smuggling in quantum mechanics. We are saying that, okay, this average of a single mode, time average of a single mode of the electromagnetic field is basically the time average of a single photon of the electromagnetic field, and you know that the photon has an energy of h bar omega, and this is, since this is the energy density, that is h bar omega by volume v, and that is equal to so this is a little bit of cheating, but there is no problem with this cheating, you can do it. So we will get 2 pi c square, and this fixes the constant A0 now. Constant A0 gets fixed to the following factor: 2 pi c square, this omega and this thing cancels. 2 pi c square, 2 pi h bar c square by volume v, and omega square root. So you have a nice expression for this, and this you can write it down in a nice way. You can write this as c 4 pi square root, and then h bar by 2 omega volume V square root. Okay, so this is how you fix the value of A0, and now you can write down. You have your expression for the vector potential with the constant, the value of this constant fixed. This is basically nothing but C 4 pi square root summation over K vector H bar is 2 omega K volume V square root. And then we have what? Then epsilon vectors. Then we have e power of I. Okay. Plus. So this is your full expression for A vector. So this is still classical, but with a little bit of smuggling in of quantum mechanics, you have a H bar sitting here. So you may say, okay, this is how can this be a classical thing? But this has nothing to do with any quantum mechanics, so to say. This is just some kind of normalization, or you can say that this is some factor that you have fixed by using quantum mechanics. But still, these are all classical things. These are classical fields. Okay. And now I would just end with one more thing, a little bit, and then we shall continue from here in the next class. So what we shall, you see from here that we have seen that this epsilon vector is a vector which is perpendicular to the direction of propagation. So this is 0. And therefore, this tells you that there are only two independent states of polarization, which is orthogonal to the direction of propagation of the plane electromagnetic field. And therefore, you can take this epsilon vector to be the unit vectors 1, 0, 0, and also 0, 1, 0. If k vector is k, say k z cap. Usually we write k cap to be the unit vector along the z direction, but I'm writing that since there are too many k's, I'm writing this as z cap. So if k vector is if the electromagnetic field is propagating around the z direction, then if you can take epsilon vector to be 1, 0, 0, 0, 1, 0. So these are unit vectors which is orthogonal to k vector. So you can basically what I'm saying is that these are the basis states or polarization states, two independent states of polarization for this electromagnetic field A vector. However, you can also have, so this is the case which is known as the linear polarization. You must have heard of linear polarization, right? Linearly polarized electromagnetic plane wave. But you can, this is not the only choice. You can have other choices also. For example, you can have circular polarization, where you can choose the basis states in the following form. You can say, okay, epsilon lambda, these are your polarization, this is your polarization vector, where lambda is denotes plus or minus, and you can say that epsilon plus is 1 by root 2. I normalize these vectors 1 I 0, and epsilon minus is equal to 1 by root 2 1 minus I 0. So these polarization vectors, these are unit vectors now. These are the basis states. You can take these as the basis states, and they actually correspond to circularly polarized electromagnetic plane wave. Circular polarization. In quantum mechanical language, you know that light has a dual nature. It is both a wave as well as it is a particle. We will see how the particle in picture emerges once you quantize the electromagnetic field. But let us assume that you know that it has a particle picture and the fact that a photon has an intrinsic spin of +1, then these states that we have written down, epsilon plus and epsilon vector plus and epsilon vector minus, these corresponds to the angular momentum projections of plus h bar and minus h bar. So these polarization states, so in case of classical electromagnetic theory, we talk about polarization vector, but when you treat light as quantum, as a quantum thing, then you cannot talk about polarization vectors, rather you have to talk about their spin angular momentum and projections of the spin angular momentum. You can see that these polarization states actually corresponds to the angular momentum projections of plus h bar and minus h bar of the intrinsic spin angular momentum of the photon along the direction of the linear momentum, along the direction of the momentum of the photon field of the photon, which basically means, it is in very simple language, you must have seen in your relativistic quantum mechanics course something known as the helicity operator. It basically tells you it is an operator whose eigenvalues basically corresponds to the direction, to the values of projection of the spin, intrinsic spin of a particle along the direction of its linear momentum. So these values plus h bar and minus h bar basically corresponds to the eigenvalues of the helicity operator that you have. Okay, so you know that the photon has an intrinsic spin of 1, and if you take the projection of the angular of the projection of that spin, intrinsic spin angular momentum of the photon, these two polarization states actually corresponds to those projections, and those projections corresponds to the eigenvalues plus h bar and minus h bar. So you see that polarization in classical electromagnetic theory actually translates to the spin of the projections of the spin, intrinsic spin of the photon field along the direction of its linear momentum. So I would like to finish here at this point. One more thing I would just like to mention is that from these polarization states, these circular polarization states that we have chosen, you can obviously see that k dot epsilon is 0 because there is no third component, so it will be 0. It's orthogonal to k vector, and from here you can immediately see that from the choice that we have taken here, we get that epsilon star plus is basically equal to epsilon minus epsilon plus dot epsilon plus is 0, which is equal to epsilon minus dot epsilon minus. Okay, and epsilon plus star dot epsilon plus equal to 1, and similarly for minus. So these are the properties that these polarization vectors satisfy. And once again I repeat, these polarization vectors actually corresponds to the angular momentum projection of the spin and intrinsic spin angular momentum of the photon along the direction of its linear momentum. which in simple, or which in mathematical language is it basically corresponds, these values basically correspond to the eigenvalues of the helicity operator, which is nothing but sigma dot p by the in case of the photon thing, we will have sigma dot p by the energy of the photon E. So that is the helicity operator. So you just note that the polarization vectors have these properties, and in the next class on Monday we shall start from here. What we have discussed is completely classical so far, except the fact that we are putting a factor of h bar here. But now, with this background that we have, we shall start quantizing the photon field. So, do you have any questions at this point? Is it okay?
Yes.
Epsilon plus dot epsilon plus. তো একটা ভেক্টর নিজের উপর পারপেন্ডিকুলার এরকম কিছু
না epsilon plus dot epsilon plus এটা নাও, you just take this
জিরোই হচ্ছে
dot will be zero.
এটা এ ভেক্টর পারপেন্ডিকুলার টু এ ভেক্টর সামথিং লাইক এরকম একটা ব্যাপার চলে আসছে না
No, it's not like that. Okay. The thing is that, see, okay, this is a good question. See, if you want to, I understand your question. It is not, see, epsilon dot epsilon is not the magnitude of this vector. Why? Because this is a complex vector. So if you want to take a magnitude of this vector, what you have to do is you have to compute the dot product of this vector with its complex conjugate, since it has a complex component. This is an important part. Had it been real, then okay, epsilon dot epsilon is a magnitude, but this is not the magnitude. Anyway, I just want to write one more equation. See, all these things you can combine it into one single equation. The epsilon lambda dot epsilon star lambda prime, that will be equal to delta lambda. You can check that, because when lambda prime this is plus and this is plus, then this is 1, and when this is plus and this is minus, epsilon star minus is epsilon plus, but epsilon plus is 0. Therefore, you have a Kronecker vector. So you can combine all these relations into these relations. So we shall use this relation. This relation will be very crucial when we shall try to compute the Hamiltonian operator for the electromagnetic field. Yes, do you have any question? Soham, Darshi, Shagor, you are okay with it?
Yes, sir.
Yes.
Okay. Okay.
Okay.
So if you don't have any questions at this point, we shall continue from here on Monday. Thank you very much.